I hope you can hear me. Just real quickly, my name is Juergen Giesow, and I will be covering a little bit on the energy side of injection molding. On the injection molding end, in the past few years, a lot of focus has been paid to the machine itself. The machine itself is certainly an essential part, but there's a lot of items around the molding machine that go into the process that really contribute to energy consumption. And anytime anything contributes to energy consumption, there's a potential for savings. So we're going to look at the machine, but we obviously look at everything around it as well, just to see, where energy is being consumed and where there's potential for savings. And here is a quick overview over what we have. We're looking at the overall process itself. Where does the energy go in and how is it converted? Then we look at the machine itself and see where on the machine is potential for savings. That being a new machine, that being existing machines. So at all of those aspects. Then we look at the mold, because the mold obviously is also one essential part. We're looking at water supply, because there's a lot of energy going into tempering the tool, and therefore there's potential there. Production planning is obviously a critical piece as well. If you can avoid downtime, your energy used per part is going down, and that's really what it's all about. And then we'll just open it up for some questions if you may have any. The energy diagram that you see here, is pretty much how we get from one end of the process to the other and what's all involved. We start with our raw material in granulate form in most cases. If it's silicone, it may be a paste, but other than that, it's in a granulate form, goes to the molding machine, is being liquefied there, cools down in the mold. So essentially what we're doing is we're converting the shape of the part. It goes from a granulate stage to a completed product. When you look at that, there is multiple aspects that go in this as well. So it's not just the molding machine. We have a dryer, potentially. We have loaders to load the material into the press, and then we go into the heating. There's different ways of controlling your heating on the molding machine. There's different ways of cooling it, and then we go at the end into the product. And when we have the rules of energy are very simple. Whatever you put in, you're going to put out. There's nothing that's lost in between. And so every energy penalty that you are that you find on your way. So if you do something not very efficient on the way in, you're going to end up getting hit again. So anything that's there has actually a twofold effect on you. So if you are optimizing something on the front end, you get a reward twice, there and on the other side of it. And we'll see that a couple times into it. When you look at injection molding in general, injection molding is a very inefficient way. Because what we're doing is we're having a raw form, we're going to get it into a solid form. In between, we're going to heat it to no end, and then we're going to cool it down to no end. So what we're really doing is there's a lot of energy there that's being consumed. So from that point of view, injection molding, if we are not careful, is a very wasteful process in terms of energy consumption. Okay? So again, in order for the process to take place, there is no loss anywhere. There's no free lunches. So when you're putting energy in, you're going to have to get rid of that energy somehow. And from a cooling point of view, either you're going to handle that by putting it out in the environment, heat up the air in the room, or you're going to dispose of it in a controlled way by using water and then manage that, some other way. If you are in an environment, in a regular plant that has no air conditioning, putting the energy out in the air is probably a very effective way to go. If you are in an air-conditioned environment, putting the energy out in the air is the most ineffective way of cooling. Because when you're going to put it out in the air, and any coolant that happens out in the air heats up the air of the room, and then it is going to be cooled down again by the air conditioning unit. So you're gonna pay extra that way. So getting energy, and especially for clean room applications, medical or air-conditioned rooms, if you can capture the energy in a liquid stage in the water of the plant, and then use that efficiently either to heat other parts of the building or to be then cooled down again outside, that is the most effective way of cooling it. Here we see, and this is now from a costing point of view, when you're breaking down your cost of product that you're making, this is a very important chart, because in a lot of cases everybody really just looks at the product and says, okay, I'm gonna multiply it by whatever factor I'm having, and that's gonna give me my output and my cost to my customer. But your input that you have to put into the system is completely different from one material to another, because the materials, they have different ways of conducting the heat, and therefore some of them melt easier, other ones melt a little bit more, need more energy to melt. We see here nylons, polypropylene, in general, semi-crystalline materials need a lot more heat, a lot more energy to melt. Amorphous materials, clear materials, such as PC, ABS, and also polycarbonate, they have a much lower heat requirement and a lower energy requirement to get into liquid stage. So from a costing point of view, especially when your throughput is high, the materials that are in the lower section should be calculated a little bit different than the material on the higher end. And that's not just from a raw material cost, that is also from an overhead cost, because your energy consumption is higher or lower, respectively, whichever one you're using. Okay, so the rule is, let's all use polystyrene for anything we make, and we're fine. We use the least amount of energy. Also, from your components that you're using, and now just categorize the molding industry into a packaging environment or a disposable environment, medical disposable, packaging, all of that falls in that category. And then we have a technical environment where we make lenses, where we make any kind of technical components that we use in the cars on our daily lives. If we categorize it in these two categories, we also find, our baseline on energy that we need per pound to melt the plastic is, let's call it on the diagram later on, it's very similar. But if we see what else goes in it, then we'll find out that our technical parts, they have a much, much higher requirement again as our packaging parts. And the reason is very, very simple. On our packaging parts, polypropylene, styrene, things like that, we put in energy and we use the water to cool it. There's no drying. There may be a little bit of material conveying involved, but it's a pretty straightforward process. If we look at our technical parts, we have a drying involved usually. We may have an elevated mold temperature, so we use the cold water and heat it up again to cool it down again at a later time. So all of that plays into the game. Then on top of that, we may have to anneal the parts, we may have to temper them, so the energy requirement on a technical part is tremendously higher than it is on a disposable part. Just from a, cost management point of view in your plant. And so the efficiency, when you really divide one by the other, you see that the efficiency on packaging or disposable part is really high compared to technical parts where the efficiency is incredibly low. Energy going in to what you are getting out. Okay, and that shows again that from a costing point of view internally, these two molding ideas really need totally different cost models. Okay, just quickly how that was calculated. Conversion, again, if we have a packaging part, our cost per converted pound or kilogram of plastic is low on our easy conversion, which is packaging, disposables, things like that. And the more technical we get, the more higher end we get in terms of requirements, the more costly it's going to get to convert a pound of material into a different shape, for all of these reasons that we saw. And that is the reason why there is one big piece of equipment in the molding process, which is the machine, why there is a lot of attention, rightfully so, paid to the machine. Now, on the machine itself, when we look at the entire process, we do have certain process requirements where we can use an electric motor in a very efficient way, and then we have certain processes where we use the electric motor in a very inefficient way. Now, the electric motor is really used very efficiently if we move a component from here to there. The motor can do that all day long, very efficient, goes here, there, back and forth, back and forth. The moment we have an area where we are starting to apply a pressure, that's where the electric motor starts to get a bit inefficient. Because what does an electric motor do at that point? It needs a constant load of current to maintain that position, to put the pressure on the system, at what point it produces a tremendous amount of heat because the motor is being stalled, and that heat is dissipated in a room that we may now need to air condition again, so we're wasting a lot of energy there. So using potentially a water-cooled motor for that, if it has to be done electrically, or using a hydraulic system in order to do that, because maintaining a pressure is very efficiently done in a hydraulic system, could be the alternatives. And that's why some combination drive machines in certain applications can be really, really attractive. Not just all electric or all hydraulic for that matter. Maybe a combination to get the best of both worlds combined together, could have some real value in it. Now, here is, the drive technology. Just if we compare an all hydraulic machine against an all electric machine, we have one motor running multiple axes. In most every case, that means we can only do things sequentially. We have to open the mold, then we move the ejector forward, we move the ejector back, we close the mold, we inject. Everything happens one thing at a time. When we look at an electric machine, we have, in a fully electric execution, we have an electric motor for each one of the functions. So since they are all independent, theoretically, we can run them all at the same time. We could open the close, move the ejector forward, and then after that's done, close the mold while the ejector is moved back. While we are still moving the mold close, we can already start injecting, those type of things. So you can really look at the molding sequence in a whole different way here from an effectiveness. Now, the really true or calculations are a lot of times done from companies that just look at your kW meter and say, okay, today I used 5 kW, and tomorrow I only used 3, so essentially I save 2. Okay, that's one way of looking at your power bill. Another way of looking at your power bill is put a relation together between the parts produced and the energy consumed. Because if you make more parts and use a little bit more energy to make more parts compared to less parts and almost the same amount of energy, you're running a much more effective process. Okay? So when you do your calculations and your study in your plant, get away from the hour meter alone, put it in a relation to the output. Because an optimized machine, in whichever way it would go, electric, hydraulic, can give you an optimized amount of output, and if it consumes the same amount of energy as before and you increase your output, you are ahead of the game. Okay, so put it always in relation to what your output is and not just on what you pay at the end of the month. The one area that we see on injection molding that is always and will still be for a concern for quite a while is this area here, the hydraulic core pulls. Because a core pull on a mold is a side action that is very easily done with an electric piston, in, out, and very cost effective done. it's a very expensive way to do it when you start doing it electric, because you have to convert the rotation in a linear motion, so if a gearbox and all of that involved makes it really expensive. Okay, so overall, we will have hydraulics in a molding plant for quite a time to come, whether that is inside of the machine or whether that is as an auxiliary unit sitting right next to the machine, providing the hydraulic pressure to run the core pulls, for example. Okay, so from that point of view, it gives you an idea that going away from the hydraulic is certainly a direction that we are seeing in the industry at the moment, but being able to get fully away, cost effective, is a whole different question. Where is the efficiency coming from? From an electric machine versus a hydraulic machine. This here shows you, what we are doing. We have a pump, a motor, a pump, a valve, and a hydraulic motor potentially, where we have an efficiency, and this is for screw rotation, because we take the rotation and the pressure that we are using or generating and then converting it into rotation again. Our efficiency factor is less than 50% on a hydraulic machine. If we take this now being done electrically, we have our motor, our gearbox, and our efficiency is really high, relatively speaking. Okay, we are at over 70%. So we have a good 20 some percent, almost 30% on energy that we just can save when we are thinking about converting just a rotation of the screw drive and use for that electrics instead of hydraulics. Okay, so even just attacking that is really a good idea, and it's just this transfer of energy. The other part is a molding machine in general works best if it is in the optimum range, and that's that number that's being published all the time as like 70% of the capacity, 60-70% of the capacity. You want to run your machine in that range. Now, as a custom molder, I know that's not always possible, but what I'm trying to say with this, bigger isn't always better. Because if you put the same product in a bigger machine, you're going to end up needing more energy to make your parts than if you put it in a machine that's optimally sized. So really focusing from a future point of view, if you start replacing machines, also focus on your sizes. There's no molding machine that can do all of the products in your plant. There's not one size that you can buy that can handle everything. There's a reason why there are smaller machines made and bigger machines made. So just make sure that you're selecting the right machines for the respective products. There's energy savings right there. Same thing, we see that right here when we get into a throughput calculation of the machine. We see our utilization and our effectiveness if we have a pack, and that's also why the packaging applications are really very efficient compared to the technical applications, because our throughput on the packaging is a whole lot higher than on our technical. Okay, so it all comes back into relation, with this chart. Here is a quick little example on a power study. We put a certain amount of power in to make a product, and this is for a packaging item. So we have our drive system, we have our cooling unit that we need to control. We give a little bit out into the ambient air, but most of it is captured by the hot water or by the water, the process water that is then being cooled down. Okay. If we look at the same thing, that's why our efficiency is at a good level. If we look at the same thing again on a technical product, we put a lot more power into the support equipment, and we end up, because of that, putting a whole lot more power or a whole lot more energy, comparatively speaking, into the ambient air and less into a water management. And again, now considering an air-conditioned environment, that is a pretty wasteful situation. So dispose of the energy in an efficient way as well. Cool with water as much as you can if you run air-conditioned. If you don't run air-conditioned, it's a whole different story. From a molding point of view, we'll just take a view now of the tool. We have our heat flow in the mold. The mold is cold, the material comes in hot. So we have two sources of energy disappearance, if you will. One is dissipation, giving it out to the environment. Second one is we capture it by the water that we pump through the mold. Whether it's hot or cold, relatively speaking, makes no difference, but we capture it, in a liquid form. And then we have also heat convection that goes right into your plates of the molding machine. And the last thing that we want to do, the molding machine is a huge heat sink. So whether you run your mold hot or cold, do not try to get the entire molding machine at 105 degrees or at 55 degrees. Try to keep that temperature in your tool. And the way how to do that is use insulator plates. Use good and thick insulator plates. And that makes no difference if that mold is running hot or cold. Because with that you keep your energy in the tool. That's where you need it. You don't need to cool the molding machine. Okay? So here is a big area that is a big contributor to energy consumption. The second thing that you see in plants a lot when we're talking about molding is water hoses. Okay? Having a manifold independent circuits to a tool for every single cooling circuit is a great thing. Gives you a lot of control. But what you do not want to do is put a manifold at the mold temperature control unit and then have a bee's nest of hoses going up to the molding machine to the mold that are 50 feet long, and each one of those hoses has this thickness and it has a lot of surface area. When you heat or cool it, makes no difference. You're going to give, through the way of that liquid traveling to the tool, you give heat away to the environment. So you're using that entire cluster of tubes going up to your tool to heat up or cool down your room, whichever way, but it's very inefficient. What you want to do is come with big water lines right to a manifold that's connected as close to your tool as you can possibly be, and then from there go with the shortest possible hoses right to your mold. Okay? So incorporate that, because now your heat loss on the way to your tool where you need it is minimized. Okay? And you see that here the water hoses, 2 inches, 1 inch, they can be calculated out however big they need to be. But that is probably, in an average molding plant, the lowest hanging fruit, that you can capture energy and gain process control at the same time by doing something like that. And this is here again, whatever you supply, you got to get rid of. So if I supply a lot of additional energy because I'm wasting a lot of energy on my way to the item that I really want to maintain, I'm having to take that energy a second time and deal with it. So that's why I have a savings that I can generate. I'm always going to get that twice, okay, on the heating side and on the cooling side. So it's, everything is times 2 on the energy front of molding or temperature control. The other item is your optimal production planning item. And there's a lot of description there. I'm going to show you another slide. Is reducing the amount of unexpected downtime. That's what this all is about. What you want to do in your molding facility is you want to keep the molding machine running, making parts, because that's when it's efficient, and then that's when it generates money anytime it opens and closes. Now, when the machine is down, which is going to happen at some point, that downtime needs to be minimized. And how can that be minimized? The minimization can happen in being proactive rather than being reactive. And there is various different ways. Have a good maintenance program. Have a good production planning program, that the machine is not sitting there waiting for the material to dry. Because you knew already a couple days earlier that you're going to run this tool today, so have the material being dried at the same time so it's ready when that tool change took place, so you don't have additional idle time on your machine. So picking up efficiency is actually going to increase your output, and that minimizes the energy consumed per product out the door. So doing something like that is really important. We have worked together with one company on a proactive maintenance program. What they did is, and just as an example, they analyzed the oil on a very regular basis. And then when they analyze the hydraulic oil, they get a report back that says we have these and these and these minerals that we find in the oil. And over time, you will find that a mineral content is going to shift. And when that mineral content is shifting, you know what component in the process is on its way out. And then with the manufacturer, you can work together and figure out what is breaking, and you can replace it before it actually really fails, and be proactive that way. And that's really the end of the presentation, and I'm running out of time. So if you have any questions on that, you can certainly talk with me in the back, but I don't want to take any other time from the person that is presenting after me. Thank you.